Hello, thank you, Emilia, for your introduction. I'm glad to take this opportunity today. My name is Timo Uluda, and I'm working as a technical marketing manager for Magic Power Modules for Würth Elektronik since October 2015. Today, I will talk about our micromodules family and their capabilities. To start, I want to give you a quick overview about the topics we're talking about, let's say for the next 30 minutes. As we consider tiny DC-DC step-down converters for space-constrained applications, we have to take a closer look at the technical requirements and the challenges that arise from these applications. The Magic micromodules have features that overcome these challenges and make therefore the design-in process much easier. These switching regulators all offer adaptive switching behavior. I will come up on this next. That optimizes efficiency across the full load current range. The tiny package approach maximizes heat dissipation while offering easy-to-route LAN patterns. Having the similar footprints and design requirements allows easy swapping between modules in the VDMM family. This is what I call flexibility through scaling. So, first, let us start with the applications and the requirements we're talking about today. Let us first take a look at these applications you see here. Miniaturized DC-DC converters can be used in camera systems, for security example, supplying the image processor IC, or analog digital converters are the essential part of measurement devices like oscilloscopes. They need a very tight regulated output voltage. Last but not least, battery-driven applications like wearables and portable devices need a highly efficient supply to guarantee a long battery lifetime. To have a common understanding about the setup of a real application, let us check the picture I have here. The application consists of an energy source, that's the black, a DC-DC converter, the red, an image sender, green, MCU unit in green, and a Wi-Fi communication devices. These are marked in gray. The DC-DC converter regulates the 5 volts that comes from the battery or the USB port down to 3.3 volts. So providing a stable regulated power to the MCU. The MCU then processes the data, initiate follow-up actions and sends commands to the sensors and the Wi-Fi module. The RF module, this is the slave here, then sends the data from the image sensor via Wi-Fi to the master receiver unit. From there, the data will be processed and visualized on a display or what else. Now, we know how a typical application is built up and which functional units are involved. With this background, now we can figure out which challenges arise here for space-constrained mobile applications. The table here shows a summary of the challenges for the DC-DC converter and how they can be solved. For example, the challenge for a battery-friendly, low heat dissipation DC-DC can be realized if the DC-DC has high efficiency. Second, this would solve both challenges because high efficiency results in less losses, meaning less energy is dissipating as heat. Based on the information, now we can build up 2 target specifications for a DC-DC converter. First, the electrical. The input voltage range, we choose from 2.5 to 5.5 volts, especially for mobile and space-constrained applications, because 2.5 volt is the minimum cell voltage for lithium-ion batteries. 5.5 is the maximum voltage offered from USB ports. To overcome the design challenges inherently in tiny DC-DC converter implementation, a rich selection of features are available within the VDMM family. This is the feature specification. Now we look at each of these features in greater detail and see why there is a need for them. First, the enable function. The enable function sets the DC-DC converter to start routine when a specific threshold voltage is reached. After setting enable high, the DC converter prepares for operation, a process that takes, let's say, roughly 100 microseconds for the magic micro module we have here. Once prepared, the module begins switching, and the internal soft start regulates the output voltage rise until the desired output voltage is met and normal operation can take place. Second, the power good function. Once the output voltage is above 95% of the internal reference voltage, the power good pin transitions from low to a high impedance state. If the output voltage is lower than 95% or higher than 105% of the internal reference voltage, the power good pin is put low. This behavior can be used for sequencing. And this leads us to the third feature, the sequencing feature. If we combine now the enable and the power good features, we can sequence multiple power modules. Each module's power good signal acts as the enable signal for the following one, turning them on in a cascading sequence. Now we come to protection features, overcurrent and short circuit protection. To shield the module from load faults, overcurrent and short circuit protection limits the output current to a safe value. If the fault is present for an extended period of time, then the module's thermal protection kicks in to prevent damage to the internal circuitry. These protection features safeguard the system upstream. To ensure the best efficiency from zero to maximum load, the switching behavior has to adapt to the different load situations that there are out in the field. Applications, as shown on the previous slides, the security cam or the wearables or the portables, do not always have the operation under full load condition. Measurement applications have a higher current demand for measuring and a lower one between the measurement points. Therefore, the power management has to be flexible enough to have the best performance for each load situation. This slide shows the efficiency diagrams of our 1.2 amp micro module as an example where we discuss now the switching behavior. On the left side, we can see, let's say, the typical behavior that we expect from standard buck converters operating in PWM mode. Forced PWM mode is widely used, and this mode is present in the majority of industrial power supplies. This mode is satisfactory for this type of application as they work in heavy load conditions for the majority of their operating lifetime. But sensor applications are different here, as we learned. Here, the light load condition is the predominant operating situation. To have here an optimal performance during this load situation, we have to modify the switching behavior. In contrast, on the right, to the PWM mode, the PFM mode shows a wider efficiency plateau in the light load area. This supports longer lifetime of the battery in a portable measurement device, for example. But these figures and numbers are, let's say, not so common to understand. So I made a small example. So if you see here, the difference between, let's say, the forced PWM mode and the PFM mode is more visible. If you see, the PFM mode starts with nearly 80% at nearly zero load, in contrast to the PWM mode, where you start with nearly zero efficiency. To make the importance of high efficiency more concrete, I use a 2800 milliamps hour capacity battery as an example. As you can see on the right, the graph, the number of days the battery will last is very much dependent on the efficiency. The efficiency between 20% and 85% is over 400% in increased battery lifetime. Here we will see the essential differences between PWM and PFM mode. On the left, PWM mode is characterized by constant switching behavior and therefore constant switching losses. In PFM operation, on the right, the inductor current is nearly zero during the idle time because switching stops. No switching, no losses. During the idle time, the load is only supplied by the output capacitor. The output capacitor discharges, which leads to a voltage drop. Then the idle time ends when the output voltage drops below an internal threshold. Then the switching starts again. The higher peak inductor current value present in PFM mode result in an increased output voltage ripple. The difference here in ripple between the two modes is clearly shown in the graph. You can see we have got here a difference of 59 millivolts between forced PWM mode and PFM mode. As the load regulation is dependent on the value of the output voltage, an increased ripple will also result in a wider tolerance window of load regulation. This behavior is only present in PFM mode, and the graphs show that once the module transitions out of PFM mode into PWM mode, the load regulation becomes much tighter. Also, the response of the module to a transient load event can be adjusted by the feedback capacitor CFF. CFF acts as a frequency-dependent bypass capacitor. The speed of the transient event is inversely proportional to the apparent resistance of the capacitor. The two graphs on this slide show undershoot on the left and an overshoot on the right. Power saving mode, PFM mode, and forced PWM mode both have advantages and disadvantages. Based on efficiency, output voltage ripple, and EMI. The best mode of operation is dependent on the needs of the application, as shown by image on the bottom of the slide, where you have got the wake. Switching current loops that act as antennas are the source for radiated emissions. Everybody knows this. Due to the tiny solution size of the modules, the effective antenna structure could be minimized. Therefore, the modules pass the EN 55032 without the need of any external filter. So how we realize this? We have here two package approaches. Both offer easy to route land patterns and excellent thermal characteristics. On the left side, we have vertical integration. This is an open frame design with the inductor taking the role of the substrate. The IC and internal capacitors are mounted directly on top of the inductor. On the right, the side-by-side approach uses an overmolding technique to encapsulate all the components and create a single, uniform body. The components are attached side by side to a PCB-like substrate, and the component side of the substrate is then covered in the mold compound. As you can see, we have here a power density of 0.65 watts per cubic millimeter, or on the right, 0.81 watts per cubic millimeter. This is why we call it tiny and powerful. The layout optimization is, for everybody, clearly known, the essential for all power supplies, as well as for power modules. The VDMM family allows for a very simple routing approach. Internal thermal layers are unnecessary, allowing for a two-layer board solution. That means one top layer, one bottom layer, and this it is. All of the features and benefits I have described up to this point culminate in a family that covers a wide range of applications. We have here 4 dimensions of scaling, we call. The first dimension for us is the package scaling. That means the same footprint. Due to the matching package, the designer here has the freedom to evaluate the application from 600 milliamps to 1.0 amp by simply changing the power module. Take the 600 out, put the 1 amp in. The layout here stays the same in both options, with a minor change in the layout to accommodate the power good feature of the other one module. A third module can be seen as nearly pin compatible. Second scaling, the power scaling. Nowadays, applications are constantly demanding higher power levels with decreasing board space. For rising power demands, the designer can choose to get from 600 milliamps up to 1.2 amp in a tiny, very, very tiny form factor. Third, the pin-to-pin scaling. For a 100% one-to-one replacement, the designer can choose between 600 milliamps and 1 amp power modules. Feature scaling means, depending on the specific needs for an application's power supply, the designer can choose between output voltage, status monitoring, that means the power good, and active efficiency control, which is called mode PFM/PWM. All of these applications you see here and examples discussed today can be realized using our power modules in a quick, easy, and very, very reliable way. Each power module here has unique strength that allow it to meet many different requirements of a wide range of applications. So all of the numbers we spoke about in the webinar are also available in our online tool RedExpert. RedExpert gives you an overview about the thermal behavior and how to choose the appropriate board space for proper heat dissipation. For a hands-on experience, an evaluation board can be ordered from our online catalog. The land pattern and physical dimensions are available for download and can be used with Altium, Eagle, or other PCB design tools. So, thank you for joining this webinar. I hope I could give you some insights and practical guidance how to use our power modules, which applications we can cover with, and I will gladly answer any question you have now. For any question that I'm not able to answer now, please feel free to contact our technical support hotline. We're happy to support you. So, thank you.